Alright, so this time we're doing problem 26 from chapter 5. The problem says, in a laboratory experiment on friction, a 135 Newton block resting on a rough horizontal table is pulled by a horizontal wire. The pull gradually increases until the block begins to move and continues to increase thereafter. Shown figure. The figure shows a graph of the frictional force on this block as a function of the pull. Part A identifies regions of the graph where the static friction and the kinetic friction occur. So this is kind of my rough replication of that graph. And so this region is the friction of static, and then that region is the friction of the kinetic, because this is a representation of the frictional force versus the force that's pulling the block. So part B then asks, find the coefficients of static friction and the kinetic friction between the block and the table. So for part B, we know that the friction of static friction is going to be equal to mu times the normal force. We know the friction of the force of static friction, that's 75 newtons from the graph. We don't know the coefficient, but we know that the normal force is going to be equal to mass times gravity. So we know that 75 is going to be equal to coefficient times the force of the block, because it's the force of the block resting on the table, which would actually be, instead of its mass, that would be its weight, which is the mass times gravity. We just plug that in here, and then we would just solve for that. So mu is going to be equal to 75 divided by 135. When you do the math, that comes out to 0.55 for the coefficient of static friction. You're going to use a similar equation, but for the kinetic friction, it's going to be equal to the coefficient of kinetic friction times the normal force, or the weight, 135. And we also know that once it starts moving, the frictional force levels off at 50 newtons. So mu of K is going to be equal to 50 divided by 135, which then equals, once you do the math, 0.37. So this one's your coefficient of static friction is 0.55, and your coefficient of kinetic friction is 0.37. The problem then asks, why does the graph slant upwards at first but then level out? So you have this slant here because as they're increasing the pull on the block, but before it actually moves, you're increasing the force that you're pulling with, and that is increasing the force of friction. And so it slants upward because they have a linear relationship. And then once it moves, the graph drops down and you get a straight line for the frictional force, because that's going to stay constant no matter how much you increase the force pulling the block, it'll stay the same. And then part D asks, what would the graph look like if a 135 Newton block were placed on, brick was placed on the block? So if we had a block from part 1 and then we added another one and we still were pulling on it, the graph would look identical except for that the values would be changed. So this graph would would still look the same, but instead of being at 75, because this force would change, but the coefficient would stay this force would stay the same, or no, that force wouldn't stay the same. That force would double. And so, because this doubles, it would be twice as much for both the kinetic friction, the kinetic friction and the static friction. And so the coefficients would be double.